Suppose your friend gives you 5 chocolates to start with and promises to give you double the previous amount every minute for the next few minutes. Fill in the table. Well, many people could realize, well, they start right away with 5, and then every minute they get twice as many, so the amount you have doubles again and again and again. You'll notice it jumps from 4 to 10 here, so I need to do some mental computations. Let's see, so the first one I started with 5, and the second one I started with 5 times 2, and then I had 5 times 2, and I doubled that, and then I had 5 times 2 times 2, and I doubled that. So this is for 0, 1, 2, 3. And so I might start to see a pattern here. It looks like I'm multiplying by 2 more for each one. Another thing you might notice is this is the same. So let's say I'm multiplying by 2 more each time. So for the first time, I'm not multiplying by any 2s. That's 0. For 1, I'm multiplying by 2 once. For 2, I'm multiplying by 2 twice. 3, I'm multiplying by 2 3 times. And 2 multiplied 3 times can be represented as 2 cubed. 2 times 2 times 2. So this is just 5 times 2 cubed. This is 5 times 2 squared. 5 times 2 to the first. You might think of this as 5 times 2 to the 0. 2 to the 0 is just 1. So the general pattern, if I want to get 10, I'm guessing would be 5 times 2 to the 10th. And what's that? Let's see, 5 times 2 raised to the 10th. 51. 20. And what about to the 15th? 5 times 2 to the 15th. It starts to get really big, 163,840. And generally what we're talking about now is the amount you have of chocolates is equal to 5 times 2 raised to the t. So for any given t, I can sort this out. This is an exponential growth function because it is getting bigger. You're getting more each minute as opposed to less by an exponential amount. So to plot this, at time 0 I'm at 5, time 1 I'm at 10, 2 20, 3 40, 4 is 80, and then I won't be able to fit the rest. And many people look at this and say, oh, well, it's a parabola. Not quite. So let's look at what the parabolic would look like. Maybe I'll do it in green highlight. So suppose we were trying to graph y equals x squared plus 5. So we'll even start in the same place. So that would start here. And if I were to just create a table here of values, x, y, at 0, I'd be at 5. At 1, 1 squared is 1 plus 5 is 6. 2, I'd be at 9. At 3, I'd be at 14. So let's plot those points. 2, 9. Sorry, at 1, I'd be at 6. I don't think the highlighter's going to do it. It's a little too thick, so let's do red. So 6. At 2, I'd be at 9. 3. I'd be at 14. What about a 4? I'd be at 21. So now it starts to grow a little bit. At 5, I'd be at 30. 6, I'd be at 41. I'm just squaring the number and then adding 5. 7, I'd be at 49 plus 5, 54. So you can see it's starting to grow a little faster, but it's not going to be the same. And it's not a skinnier parabola. It's an exponential function. So this follows exponential growth. And that's what an exponential growth function looks like. So how many chocolates would you have in 42 minutes? Well, you simply just use your equation. The amount is equal to 5. And then doubling for 42 minutes. And 5 times 2 to the 42nd is, my calculator says 2.199023256 E13, which is times 10 to the 13th. Which, if you want to move the decimal, you'd move it 13 times. 6, 9, 12, 13. So 4 more on the end. So 2.1990232560000. So that would be million, billion, trillion, 21.99 trillion chocolates. A lot of chocolates. When would you receive 500? Well, that's a little more difficult. So right now, so I want the amount to be 500, and that's equal to 5, 2 to the t. I can divide both sides by 5 and get 100 equals 2 to the t. But I don't have any mechanics right now for solving this, so I would have to start guessing. So 2 raised to the 6 is 64, 2 raised to the 7, 128. 2 to the 6, 64, 2 to the 7, 128. So I know it's in between those. Let's try 2 to the 6.5. 2 to the 6.5 is 90.5. So it's a little bigger than that. 2 raised to the 6.6. 97. 2 raised to the 6.7. 103, so that's too much, so I know it's between 6.6 and 6.7 minutes. I might stop there and just say between 6.6 and 6.7 minutes. But if you want something more exact, let me introduce this idea that won't come up, till Algebra 2, but why not? So here's the idea. It's called logarithms. The idea of logarithms is that this expression here could be rewritten as a log base 2, since 2 is the base of 100 is equal to t. And this can be rewritten due to some log properties as log of 100 over log of 2. Now this is useful because we have a calculator that can compute log, just log, and when I say log I mean log base 10. So log of 100 divided by log of 2 tells me the time is equal to 6.64385619. So it was between 6.6 and 6.7, it was 6.64385619. So again, in this problem, we started to introduce the idea of exponential growth and be able to come up with equations based on a scenario and use that to abstract to find other amounts after certain minutes and possibly how to guess at certain minutes for certain amounts.